back for the holidays. Basically, we are going to start talking about relativity, general relativity right now. Well, equivalence principle. Okay, so before we went on a long holiday, we pretty much completed the discussion about special relativity. So everything we know, everything is clear. And as we said, there was, I'm not going to repeat everything. If you have questions, then you come to me or just homework. And as we say, the problem with special relativity is that it did not contain any gravity. Let's talk about four vectors, velocity, separation. Now we are interested in understanding gravity. And what's going to happen is that we're going to see very shortly that all the formalism that we develop is going to turn out to be very useful in general relativity. Now, in fact, there are two questions that we want to answer. So the first question is, how does the existence of matter curve space-time? So the whole philosophy that I told you is that the space-time is not flat. It's not Minkowski, but it's something else. It's curved. And so the first question is, how does the existence of matter, but also of course of energy, is equal to mc squared, or energy acts to curve space-time. I shouldn't use quotation marks. Curve space-time in the sense that it is non-Euclidean, non-flat. And the answer for that is given by Einstein. That leads us to Einstein's field equation. And the second question is, how do we describe the motion of particles? And for that sake, I also refer to as photons, massless particles, in curved space-time. So how do particles travel in curved space-time in such a way that we as observers say that they are influenced by gravity. Such a way that we call their trajectories as influenced by gravity. Essentially, we want to answer these two questions. And you want to do it like from really basic physical principles and basic mathematical principles, which is what we do. It's going to turn out that answering the second question is much easier than answering the first question. So we're going to first answer this question and only then develop the full formalism that will enable us to solve that question. Because this will require us to dig much deeper into what do we mean by curved spaces and how do we describe them mathematically. Okay, so that's what we're going to do from here on. So the next few weeks, actually I should say, we're also getting into we're going to have a slight break, which is not exactly expected, or partly expected. So we have a lecture today, Thursday. We have a lecture on Sunday, as usual. Next week, Thursday, there will be no lecture because of Independence Day, right? The following week, we will also miss 2 lectures because I will be abroad. Also, Shai, the tutorial will be abroad. So this we can compensate for these 2 lectures down the line. That means that there will be like nearly 2 weeks of break again. This Sunday there is a lecture. Okay. Questions? Or what are we going to do? So where do we start? What is the starting point? If I ask you, that means that I expect that you may know what's the starting point.
Maybe we need to define what is gravity exactly. Is it force or not?
And again, it's not a force. Actually, it's written right here. In general relativity, gravity is not a force at all. It's curvature of space-time. But what is the starting point? Where would Einstein begin? Said. I wouldn't ask you if I wouldn't say that already. The starting point?
No, it's weak.
What?
Weak principle.
Which is what? Don't know what it is.
Meaning that the gravitational mass and the acceleration mass is actually the same.
Right. And who said that? Who showed that?
Switch
What was? Right. Remember that. And I told you, at the end of the day, physics is an experimentally based science. The experiment is that of what Fosh. What did you ask us to read about? It said that the gravitational mass, mg, is equal to the inertial mass, mi. And because this is so important, this is sometimes referred to as the weak equivalence principle. So this is experimental fact. Referred to as the weak equivalence. It's 19 principles. Every place there is a gravity that appears in the equation, you can always replace it by an acceleration due to another force, which had nothing to do with gravity. Right? That is because the coupling of matter into gravitational field, right, is always the same, as opposed to, for example, to the coupling of matter to electric field, which we called charge. Some particles, different particles react in different ways when they're put in the vicinity of an electromagnetic field. Some particles have zero charge and they don't care. Some particles have positive charge, some particles have a negative charge. As opposed to that, all particles react in the same way when they're being exposed to a gravitational field. That's just what that is. Not much. It's an experiment. And that means that if we're in a freely falling elevator, right, so we have a big tower, Burj Khalifa, right? There's an elevator inside the tower, it's now freely falling. There are physicists that try to read falling. physicists now try to measure gravity, they can't do it. Okay. Because gravity is cancelled from all the equations. Okay. So, the freely falling elevators, freely falling elevator, gravity cannot be measured. Put a star, because I told you this is not exactly accurate. Why not? You actually can measure gravity if you try really, really hard. Why? Imagine yourself in a freely falling elevator. Ask you to measure gravity. Additional. Do you know that you're in a freely falling elevator at all? Maybe you're just flying there in space.
Do we have a window or something?
No, you don't have it. You have no window. You cannot look outside.
The
Why do I-
direction of gravity is not exactly the same because it's towards the center.
Exactly.
So
Exactly.
it's-
Right. So if you wait long enough and you have two physicists, and as they go down, they could measure that they're getting closer and closer together. Right? Because they're both attracted toward the center of so toward the same point. So that the gravitational field is not pointing in the same direction. Right? But this is, of course, a second order. Right? So if the gravitational field of Earth was uniform, of course, we wouldn't do that. So what it really means is that we cannot measure in a small enough region of space. How much is small enough? Infinitesimally small, depending on how well our measurement capabilities are. Okay. So, based on that experiment, Einstein postulated an even stronger statement, principle, which states the following. This goes to Einstein postulation. It says the following: at every point in arbitrary gravitational field, it is possible to choose a locally inertial coordinate system such that within a sufficiently small region of points, the laws of nature take the same form as in unaccelerated Cartesian coordinate system. This is known as the strong equivalence principle. short, simply the equivalent principle. When we say equivalent principle, we mean that. What does it mean? What did it say? Let's say I'm in some arbitrary gravitational field. I don't know how this field looks like. I don't really care. But what does it say? Let's say this is the Earth. So I'm here somewhere. Okay? Some point. There is always a freely falling system. Right? So let's say I like to jump out of planes. You jump out of plane. I'm freely falling. If I'm in a different location, right, the freely falling system will be different. Right? If I'm in Australia, right, then my freely falling system will be in this direction, basically. But I can always go to the freely falling system, and in that system, everything we said about special relativity holds. So we don't need to throw it away. It's true, locally. Okay? It's not the same freely falling system here and in Australia, right? But locally, I can select a point, and then it's always possible to have a freely falling system. That is what this is.
Why it's inertial?
What?
Why it's inertial?
It's inertial. In the freely falling, it's inertial. Think of I'm jumping out of an airplane. I did not yet open the parachute. I'm just freely falling. I'm not moving in my system. Well, there is air, of course.
But your speed changes.
I'm looking at my system. My speed changes relative to Earth.
Yeah.
Relative to myself, I'm not changing. Nothing's changing. If I'm in the elevator, can I measure my change of speed inside the elevator? No. You're looking from here, say, oh, this is. I don't know about it. Right? This is exactly a direct consequence of this Gaussian experiment. I can always select freely falling coordinate. Locally inertial. Switch to term locally inertial is freely falling. Right, there is always a locally inertial. It has to be local, clear, right, from here and from Australia, it's all the same. So I can always find one. So I can always cancel gravity by just selecting a system that will be freely falling, and in that system everything is locally inertial. Fine? Yeah? Cool. So, the loss, regardless of what gravitational field I am into, subject, right, there is always the laws of special relativity hold locally in that inertial. Laws of SR hold locally. Inertial. Now, if you get that, this already strongly suggests that the whole effect of gravity would be attributed to the change of space-time from being flat to being curved. Right? Because what we really care about is the difference between this point here and this point here. It's not exact, it's not the same. It means that there is no such thing as a global suppose, remember, we talked about that Newton thought of this absolute frame. So here there is none. When I have gravity, there is a gravitational field that attracts space. So in every point in space, I can select a locally inertial frame, but these local frames are not the same frames. Again, easy to visualize. Freely falling parachuter, free parachute here and in Australia. It's not the same frame, but they feel the same.
Can I ask you a question?
Yeah.
If laws of physics in both systems are the same, right? How you can distinguish this is not the same?
So it's locally.
Yes.
So locally. So locally, the laws of special relativity that we spent a few weeks talking about, they hold locally. No problem. Don't worry, by the end of this lecture, we start getting answers to your question. Yes?
But this is not true, let's say, for electric field because the charge is not equivalent to potential.
Because different materials will react differently. But here I don't care. All masses behave the same when they are subject to a gravitational field. Okay. Now, if you understand this idea, that automatically gives us one consequence, which is not there in classical mechanics, but is there in GR, which is a gravitational redshift. When we say redshift, I want you to pay attention. There are we refer to two different types of things. One is called a gravitational redshift, and the second is called a cosmological redshift. Cosmological redshift comes from the expansion of the universe. Now we're talking about a gravitational redshift, so it's not the same, but in fact it's still a redshift. Let's see what it means. Gravitational redshift. Okay, so let's make an experiment. This is the floor. We're right here on the class. Right. And we need to switch a light bulb. So we put the ladder. On top of the ladder is Alice. Because we're in Israel, and let's call it Ayala. It's going to be an A. At the bottom of the ladder, there is a Benny. And they're on the Earth, so there's a gravitational force, acceleration, which is called G, and the height here is H. Now, let's say I want to tell something to Ben. Give me the line or something. How does she signal him?
Shouts.
Yes.
Speaks.
Yeah, but of course she's physics, right? She'll send him a photo. She's trying to send, so she sends him a photon, and then she sends a second photon after some time. Right? Which will go delta tau eta. Then when you receive the photons, the time difference between the receive of the first and the second photons is of course delta tau Benny. Now I'm arguing that because of the equivalence principle, always delta tau Benny is going to be smaller than delta tau Ayala. The time interval between this received of the two photons sent by Ayala is going to be shorter when measured by Benny than the one that was sent by Ayala. You see that?
Is that the acceleration of G?
Because, exactly because of the acceleration. So one way to think of it is that because they're both in a continuous acceleration of the gravitational field, then Benny receives the signal when he's moving slightly faster than Ayala was. The way to think of it, remember, instead of G, they're both here in the class, right? We can say, what happens if we take this class and we put it in a spaceship, which is floating somewhere in space? And then there is a captain, and the captain turns on the engines of the spaceship. These engines produce an acceleration which is exactly equal to G. What will happen is that by the time Benny receives these two photons, he will be moving slightly faster than when Ayala was when she was emitting these photons. Actually calculated. So, because of the acceleration, Benny receives photons when he's moving faster than when they were emitted. That's a little calculation. We're going to do a very simple calculation and ignore second order terms. Ignore second order terms. Namely B over C squared. G over C squared. We're going to ignore this because we don't care, they're too small. So let's say that this is the z-axis, right? So this is z-axis. Now everything is one dimension, only on the z-axis. And we said that Ayala is on the top of the ladder, so she is at height h. So Benny's location. Benny's location. Set Benny as a function of t. Is the what? Half g t squared. And on Ayala. A t is half g t squared. So let's say that ILR's first photon was sent at t equal to 0. So remember, we talked about events. Right? So 1, ILR sends at photon at first photon at t equal to 0. Okay. Then Benny receives photon, first photon, at time t1. Okay. And what do we know? Z ILR at t equal to 0 minus Z Benny at t1 is equal to what? Is equal to what? Photon is moving.
Speed of light.
What? Speed of light. So, what was the distance that the photon moved? What was the distance that the photon moved?
H minus.
CT1.
Oh,
CT1. Thank you. So, H minus half GT1 squared is equal to CT1. Yeah. Now for the second photon. Second photon, ILI meets the second photon. We're talking about a third event. ILI meets second photon at time what? T is equal to delta tau ILI. And Orange Benny receives second photon. At what time? What time?
T1 plus delta tau B.
T is equal to T1 plus delta tau Benny. Right? So, what do we have? Z ILR at delta tau ILR minus Z Benny at T1 plus delta tau Benny is equal to what?
C times T1 plus delta tau Benny minus delta tau.
Very good. Equal to C times T1 minus delta tau Benny plus delta tau ILR. Sorry. Plus minus. So, Z ILR, delta tau ILR is H plus half G delta tau ILR squared minus Z of Z Benny is half G T1 plus delta tau Benny squared. Is that T1 plus delta tau Benny minus delta tau ILR. Okay. So H plus 1/2 G delta tau ILR. So H here. Yeah, I just opened that. So minus 1/2 G T1 squared minus G T1 delta tau Benny plus half G delta tau ILR squared minus delta tau Benny squared is equal C T1 plus delta tau Benny minus delta tau ILR. this is going as delta tau squared, and we assume that delta tau is small, so we can neglect that. This would go as G delta tau squared. So it's H minus 1/2 G T1 squared minus G T1 delta tau any. It's approximately C T1 plus delta tau any minus delta tau iota. Now you can take this equation and subtract it from here. So H minus 1/2 GT1 squared is equal to CT1. To the left is minus GT1 delta tau any is equal to C delta tau any minus delta tau iota. What is T1? I can approximate it. T1 is approximately H over C. There is a correction. It's again the second order. So throw it away. And I eliminate here, and this is here, and we get delta tau any is equal to delta tau iota divided by 1 plus G H over 6. This is always written. This is about delta tau iota 1 minus G H over 6. Which is I promised you. Delta tau any is always smaller than delta tau iota. Now we did this calculation for any and iota being in a spaceship that is accelerated at some acceleration a. But equivalent principle tells us this is exactly the same thing that happens when they are here on Earth, subject to the force of gravity. To be a little bit more sophisticated, what is GH, by the way? Do you recognize that? Somebody showed it to you. It's a difference. Yes, this is the difference in gravitational potential. Very good. So you can write it down as delta tau any is delta tau iota 1 minus delta phi, difference in gravitational potential divided by c squared. So the receiver of the signal, right, value was on the bottom of the ladder, so it was deeper in the gravitational field, deeper inside the gravitational potential. And so delta tau for him was smaller. Okay. If it was the opposite, if Benny was trying to say something to iota, he's in a deeper gravitational potential. She is at a smaller gravitational potential. Right? And the time interval that you will receive is longer. Yeah? Very nice and very simple effect. You need the kindergarten math. Right? This was demonstrated, if you maybe you heard of this, first time it was seen was by Paul Bebka experiment they did it in Harvard. They went to one of the tall buildings. It was in 1959. It had a laser, so it had a laser. Just check it out. It's the first time that this was seen experimental. Obviously, otherwise we wouldn't speak about it. Instead of time, we can speak of crests of light wave. Right? We have light wave, which is a wave, right? It has crests. So you can think of that as a series of signals. Right? So if we have a star that emits light, you can look at the light wave, look at the different crests of the star, you can look at the time between these crests. Okay. Of course, what is the inverse of the time? Frequency, right? So what will happen to the frequency when we get out? If time gets,
It will shift to red.
it will shift to red. Exactly, right? So nu causes delta tau to the -1. Nu causes delta tau to -1. So if a light is emitted at frequency u star from the surface of the star, it will be observed by a distant observer at frequency nu infinity. That's exactly what is written here. Like nu star minus delta phi over c squared. If you were to be a little bit more sophisticated than what we wrote here, then it will be n star 1 minus gm over r c squared. That's it. Of course, this is only true for first order. There will be corrections. Everything we did, we just throw away in second order terms. This is true for first order. It's actually quite a good approximation. So the observed frequency, this is us, right? We are the observer at infinity. We are looking in the telescopes at some stars. The stars emit light. Right? We watch these light, and we're seeing it in frequency, which is smaller than the emitted frequency. Right? This is called, lower frequencies are the red part of the spectrum. This is why this is called, in other words, you can say that lambda, which is c over nu, increases. So lower frequencies, this is equivalent to higher, larger wavelengths. And let's call it redshift. This is the origin of the term, and I note again, when we speak about redshift, this is a term that you likely have seen in the past. There are two, we refer to two different things. We already talked about gravitational redshift. There is also a cosmological redshift, which we will talk about closer to the end of the semester. Okay. Now I made a small table just to give you a feeling of what we're really talking about here. So, just to get the feeling of the object, radius, centimeters, mass in grams, then you can calculate what is gr over gm over r c squared, potential. So Earth is the radius of the Earth. Only one I expect you to know, even if you're not a astronomer.
6,100
Kilometers, right? So because we want centimeters. How many centimeters?
4.8, 6.4.
Centimeters. What's the mass of the Earth? Do you know? Grams?
Kilograms.
Kilograms.
Yes.
Not bad. 6 times 10 to the minus 27. So 6 times 10 to the 27 grams. Roughly, so if you put the numbers, you find out that GM over RC squared is 10 to the minus 9. So that's why it's legitimate to remove all the second order terms when I'm talking about Earth. Where, by the way, you may know this is actually required.
Maybe GPS.
Yes. Right. GPS, which today everybody carries in his cell phone in your pocket. If you don't compensate for that, it's gonna be it's not gonna work after a few hours. You're asked to calculate it. Now let's go for other objects. Sun. You know the size of the sun, roughly? It's 10 to the 11 centimeters. So that's much bigger radius. What's the mass of the sun? Right, you know. How bigger the sun is?
Maybe million?
Hmm?
Like 6 orders of magnitude?
No, not too bad. Something like 10 to the 33 grams. So if you calculate what is GM over R squared for the sun, that's 10 to the minus 6. That's still it's much bigger than the Earth, but not that. And we can speak about white dwarf. That you know if you took a course in astrophysics. What's the size of the white dwarf? No, it's about 10
Light
to the
years.
Earth. It's about light years, not too far from the Earth. What's the mass of the white dwarf?
Like the
Like
sun?
sun.
Like the sun. Something like the sun, 10 to the 33. And so the potential there would be 10 to the minus 4. So this is still legitimate to use this approximation. And the last one of interest is a neutron star. What's the size of the neutron star? You know?
Maybe like a move. Then
Actually, yeah, that's not too bad. So something like 10 to the 6 centimeters. 3 orders of magnitude less. Moon is much bigger. Much smaller. 10 to the 6 centimeters is a what? It's like 10 kilometers. Like big city. What's the mass?
like a sun.
Like the sun. So it's the same star that collapses roughly. 33. And here we get into the minus 1. Potential. If you're watching neutron stars, well, the correction is still 10%. It's still not that great, but it's there. Definitely things that can and are being observed. All right, questions?
Well, you know, what happened? GM over us. Well, it's a good point.
What happens?
Like we never reached this.
Like
What
home.
we get? Black hole. We'll get to it. But again, the correct answer is then this approximation that we said earlier fails. We cannot use this very simple calculation that I just did. Yes.
You just said the approximation fails. Is it even less general than that? Because the gravitational potential in the first place was the same if the mass was equal 1. Right? So that's the way that we know it from classical mechanics. The MGH term, you just took the GH and you turned it into
That made it a GM over R.
Yeah.
Yes. Yeah,
No, so the question is what happens, because this is also the, I'm just curious if like I had something very massive and something very massive instead of, what's it called, to them being like on a ladder. If one is on this planet and one is on this planet and they're very close, this also like wouldn't hold in a case like that.
The principle will hold. The exact calculation may not hold. The idea here is to show you we already encountered an effect without doing nothing really, just accepting the equivalence principle. We already encountered an effect that is not there in classical mechanics, but is there in GR, and is there of course observation. I just mentioned that already in the 50s people actually measured it on Earth, and astronomers see it all over. If you want to become an astronomer, but I know about this effect. Okay. The full calculation we will do. Right now, this was just a simple demonstration, very basic one to show you that we already starting to encounter effects that are not classical, something which is new. Right. Hope that answers, and you'll get a complete answer before the end of the semester. You have to stay here several more weeks. Right? More questions? No? Okay. Now we're going to start here at our hands. Reading everything. So far, it's just playing in the set games. Okay. Mathematical description of curved spacetime. The example we gave was very much counterintuitive. Right? You wouldn't expect it. We did initially when I asked you what is times and age. Why was it counterintuitive? We had two photons. They followed exactly the same trajectory. Yet, the time difference here, delta tau ayala, and the time difference here were different. Although they traveled exactly along the same trajectory. So this already suggests that the real effect of gravity is to modify space-time from not being flat, being something else, curved. Okay. Although photons, the two photons followed exactly the same trajectory, delta tau ayala was different than delta tau. Right? And that basically leads us to the idea that gravity acts to curve space-time. In the presence of gravity, space-time is curved. We're going to continue with this assumption from here and see where this leads us. And then the second thing is that in the weak equivalence principle, we claim that even though space-time is curved in a small enough region of this curved space-time, the laws of special relativity hold. So what we're going to do is see where this leads us. So we select an arbitrary point in space-time. And we said in this arbitrary point, there is always a freely falling system. So let's write it down. So we sat at this point. We set a freely falling coordinate system, which we call psi. Psi alpha. And we said that in this coordinate system, the laws of special relativity hold. The laws of special relativity. Fine. So, what is the proper time? Write it down. Theta squared is what? You know.
Gamma.
Theta squared is
Yes.
yes minus 1 over 6 squared. Yeah,
Delta x squared.
exactly. Eta alpha beta, B psi alpha, B psi. Now we said this coordinate system is locally inertial. This is a locally inertial. It's a locally inertial. Which means that if there are no forces acting on the particle, what's the trajectory? What's the equation? Its trajectory?
Straight line.
It's written as what equation?
Straight line.
Yeah. What is the equation?
Psi.
What is the equation of a freely falling particle, freely falling system?
Second derivative. Psi is 0.
Yes. With respect to? That's Newton's first law of motion.
Proper time.
du alpha, use capital N. Use a different du alpha over the tau is d squared psi alpha over d tau squared is equal to 0. That's Newton's first law. Alpha is big psi alpha. Okay. It's a four velocity. Okay. Now I'm going to do something. That's it. That's the important point. What I'm going to do now, I'm going to do something which is purely mathematical. There is no physics. What I'm going to say. We'll go back to the physics. Right now, what I'm doing is completely mathematical. I mean, who sees that? Let's say that you are now jumping off a plane, right? Like these three jump right now. Call it three jumpers, and then there's a friend coming with you with a camera, right? That takes your picture while you're floating in the air, whatever, dancing in the air, whatever you want to do. This is the correct way of thinking. Okay. What the camera sees, nothing, right? You're just moving in a straight line. Nothing happens. Now I'm asking asking, okay, let's look at some different observer at a different coordinate, which may see you accelerating. Okay? Any arbitrary. Okay. Completely arbitrary, it's completely mathematical. So, now consider an arbitrary coordinate system. Which I'm going to call x mu. In that system, it doesn't have to be inertial. It's general. So you may see this really falling as not really falling, it's being subject to gravity. But right now we're just doing a completely mathematical game. So I don't care about physical interpretation. We'll get to that later. Okay? What is the proper time in this arbitrary coordinate system? So in this new arbitrary coordinate system, so now I want to express the old coordinate xi in terms of the new coordinate x. Yeah? So d tau squared, well, so you see, eta we say it's just a simple matrix. Now I want to work in the new coordinates, so I write it down as d psi alpha over dx mu, dx mu, use partial derivatives, right? D psi beta over dx mu, dx mu. I just did this change of variables, that's it. Which I can write it down as minus 1 over c squared g mu nu dx mu dx mu, where I define g mu, the matrix g mu nu, to be eta alpha beta d psi alpha over dx mu d psi beta over dx mu. Mathematically, I did everything is totally legal here. G nu nu, of course, has a name. How do we call this? This is a metric tensor, but arbitrary coordinate system. Right to do that. I can't do anything. Just change coordinates. I can look at my freely falling particle in any coordinate I want. Okay. Now I'm arguing. Here I don't see any acceleration. But in the new coordinate system, I will see an acceleration. How does it look like? Well, let's see. In this new coordinate system, a really falling particle, will look as is accelerated. So let me show you that. Well, we have this equation. This is the equation of a free falling motion. Right. So let's write it down, but now in the new coordinate system. Well, 0 equals du alpha over beta. But I want to express that in the new coordinates, x, not xi. So this is d over d tau. Okay. U alpha is d xi over d tau, d xi alpha over d tau. So I want to express that in terms of the new coordinates. So write it down, d xi alpha over dx mu, dx mu over d tau. Again, this is a partial derivative here. There's only one tau, so there's no need for a partial derivative here. So again, d over d tau, I have two terms here. So let's get d over d tau of that part. Write it down as d squared psi alpha over dx mu dx mu times dx mu over tau. This is that times dx mu over tau. Plus, now taking the second term, so d xi alpha over dx mu times d squared x mu over d tau squared. So it's going to get ugly very quickly. Let's say equal to 0. Now to make things simple, I'm going to multiply that by the inverse of that. So d psi dx lambda, let's say d psi alpha, and then I'm going to use the fact that d psi alpha over dx mu dx lambda over d psi alpha. This is equal to what?
dx lambda over
D psi alpha over dx mu, dx lambda over d psi alpha is a what?
dx lambda over dx.
Which is a what?
Delta.
It's just delta. I'm going to call delta. Delta lambda. So I'm going to multiply that. Use that fact. So if I have a delta lambda mu, that means that I have from here 0 is equal to d squared x lambda over d tau squared. Right? The mu turns into a lambda because of the delta. Plus what I will have here, which I'm going to call a strange way, so capital gamma, and then lambda u mu. That's how you write it. This is not a vector tensor. dx mu over tau, dx mu over tau. Where lambda mu defined as second one from here, dx lambda over d psi alpha times d squared psi alpha over dx mu dx mu. Strange object, which is not a vector, not a tensor. Therefore, I write one upper index and two lower index, and I allow myself to put it one on top of the other. This has a name. In fact, it has two names. Currently, I'm going to call it, it's called the affine connection. This is called the called affine connection. This is the definition of the affine connection. What we're going to see, the reason for this name is because this is going to give us a way of connecting vectors and tensors in nearby points. Remember that we spoke about arbitrary curved space-time, like manifold, and we said that vectors belong to a point, and if you have a different point on that manifold, you cannot connect the vectors from one point to another because they live in different spaces. The affine connection is the way we're going to have to. It's a way of overcoming that. Connect vectors from one point to another one, which we're going to need. Because we're going to need to have to do derivatives. That's why it's called connection. Hey, what do we have here? What did I do? Everything is purely mathematical, and in fact, it's very simple. Right? I just took free falling particle, which is not moving, in freely falling frame, and I wrote it in trajectory. It's still free falling, but in a different coordinate system. Arbitrary. X. It's not inertial. It's any coordinate system. And what do I see? This is the same equation as this, right? But hey, what do I see now? In my new coordinate system, X. This is the one that I'm using now. What do I see? What?
You get acceleration.
Exactly. What is d squared x lambda over d tau squared? This is, right, dx lambda over d tau is the velocity, right? So this is an acceleration rate. So I get a d, let's call it u, lambda over d tau is equal to minus gamma lambda mu mu dx mu over d tau dx mu over d tau, where u mu is dx mu over d tau. So I can also write it as minus gamma lambda mu mu u mu u mu. Yes.
Why we don't left? We didn't left any spaces between indices. Before when we.
This is not a tensor.
What is
Fine connection. It's not a tensor. It does not behave like a tensor. Remember, our definition of tensors was that they transform in a certain way when we change the coordinate system, right? And the Lorentz transformation. This does not. When we change coordinates, it will not transform. This is the way it's being defined. If I have a freely falling coordinate system, psi, and my x is any arbitrary coordinate system, this is how I find it. So this is u mu. This is the 4 velocity in the new frame, non-inertial frame. 4 velocity in the new non-inertial frame. Yes.
If X was an inertial system, I expect the affine connection to be 0.
If X was a what? Freely falling system?
Yeah, it's okay.
Yeah.
How can I see it mathematically?
Just plug it in here. Well, it's yeah. It's not gonna be yeah, it's gonna give you 0. Just plug it in. Maybe you can see from here. If you're trying to take the second derivative, X with respect to itself, yeah.
The initial equation, the inertial one, and the one that you just got, there's some correction that you need to do when you're not in an arbitrary coordinate system. Is that a logical way to look at it, or is it
Well,
would you say that's wrong?
this is arbitrary coordinate system. This is a freely falling system. So yeah, you're right except for this. This is a freely falling particle, a particle without no forces acting on as seen from freely falling. Think of an astronaut that moves in deep space. Right? Today it's much easier to imagine than 120 years ago, 100 years ago. But today you can simply imagine an astronaut. Right? So, well, astronaut in this International Space Station doesn't feel anything. Right? As seen from another astronaut in the same space station, there are no forces acting. But from our perspective, the astronaut is moving. It's freely falling. Because our coordinate system is not the same as the freely falling coordinate system of the astronaut. This is how we describe the acceleration of this. One more thing to just complete the discussion here. What will happen if we're speaking of photons rather than massive particles? So if we talk about photons, for photons, what's going to change?
Acceleration is always zero. For photons. Speed is constant, right?
Mm-hmm. Well, the only thing that will change, so we cannot use tau.
That would be
Tau is zero. So we simply need to set a
Choose
different
another-
parameter, another parameter. We normally call it zero, sigma. So for photons, we have du alpha over d sigma is d squared psi alpha over d sigma squared 0. And 0 is minus g mu dx mu over d sigma dx nu over d sigma, and 0 is equal to d squared x lambda over sigma squared plus gamma lambda mu nu dx mu over sigma dx mu over d squared. Yes, photons do accelerate. Where do we see that? For example, in rotation. Let's change the controls. Depending on which frame you look. Now, more questions.
Can we say that dx mu over d sigma is just c?
No. X is a coordinate. Think of x minus z coordinates. But sigma is the parameter along the photon trajectory. So to see where the photon trajectory is going. These are coordinates. Again, it's very confusing. These are coordinates here. Right? Okay, so the next thing I want to do, the relation between the affine connection and the metric tensor. So far, everything I did here is purely mathematical. I just took a trajectory, really falling, and I just say, I don't want to look at it in simple coordinates, I want to look at it in arbitrary coordinates. X, which are not inertial, necessarily. And that's what I got. I didn't say anything about the physics. I did find this strangely looking parameter, the affine connection. And I realized that in this new arbitrary coordinate system, I do see an acceleration. And that acceleration is related to this value of the affine connection. Yeah. And that leads me to now we're going to get to a physical interpretation. So if the acceleration is due to gamma, what will be my physical intuition about the role of gamma?
It's a force.
It's a force. Which force? Gravity. That's the only thing we care about. So really, gamma has some connection, not very simple and not direct, to the gravitational force. Okay, this is it. Now, remember, right? This is no more mathematics. Now I'm giving a physical interpretation to this entirely. What we said so far is completely correct mathematically, and it's accurate. There's no hidden assumptions and there is no approximations. But now I want to give a physical interpretation. So in some way, gamma represents gravitational force. Now the time interval, the tau, is determined by G, the metric, which I erased. So that means that we expect to see some relation between the metric and the affine connection. And in fact, what we're going to show here, I'm going to show it to you in a few minutes, is that the affine connection, I can get it from the first derivative of the metric. It's actually, I can get it from the metric by taking the derivative of the metric. And we said if the affine connection gives an interpretation of a force. Force is derived from a what? Derivative of
The momentum.
no, potential. Right? Force is the derivation of the potential. That means that this matrix G actually have something to do, physical interpretation, right, with the gravitational potential. It's quite cool. This is entirely hand-waving mathematical thing. Now we're talking about some physical interpretation. So let's do it before we go home. Relation between the affine connection and the metric tensor. Take the derivative of that, so AG mu over dx lambda. Okay, d squared psi alpha over dx lambda dx mu dx beta dx mu beta alpha beta plus d psi alpha over dx mu d squared psi beta over dx lambda dx nu beta alpha. eta is a simple matrix, so I don't need to take any of its unit. Now from the affine connection, right, we had gamma lambda mu nu plus dx lambda over d psi alpha d squared psi alpha over dx mu dx d. So from that I can write down that d squared psi alpha over dx mu is gamma lambda mu times the inverse of that, so d psi alpha over dx lambda. Formally, I have to multiply by the inverse of that, and then take it as a function. Right? Just say it. So I'm going to use that. You all understand what I'm doing here? Yes. Yeah? Just multiply by the inverse of that and take it as a function, and then so I'm going to use that in here. Get that dg mu nu over dx lambda is equal to, so run out of indexes. So I have I don't want to use the nu. It's already happened. Remember, if I have index that appears twice, I can it's just a dummy index. So let's use that as row. I cannot use new. I already have here a new. So call that lambda. But one important thing about this affine connection, which is worth saying already right now, have a look that it's symmetric in mu and nu by definition. Right, so gamma lambda mu nu is equal to gamma lambda nu. You can immediately see that from the definition. So if I do that, I plug it in here, then I have gamma rho lambda mu d psi alpha over dx rho d psi beta over dx mu eta for beta. And now I need to do here the same, but with a beta. So whenever there's an alpha, I can change that to a beta. And wherever there's a mu, I'll change it to a mu. Good. So I have plus gamma rho lambda mu d psi alpha over dx mu d psi beta over dx rho beta alpha beta. I told you it's going to get ugly. You have to go very slowly, and you see that everything is in place, but you have to do it very slowly and very carefully. What's written here? What is that?
C squared minus.
It's G. It's G. Right, so this is equal to gamma rho lambda mu G what? Rho nu plus gamma rho lambda nu G rho mu. Okay, we're getting somewhere. So what we're going to do is we're going to take that and change mu with lambda, nu with lambda. subtract mu with lambda and add, and mu with lambda and subtract. So we get dg mu over dx lambda plus dg mu lambda mu over dx mu minus dg mu lambda over dx mu is equal, so I have these three terms. First term is the same, so I have gamma, got that on the row, so I just change it to kappa. Kappa lambda mu g kappa mu plus gamma kappa lambda mu g kappa mu. That's with that. Now this is the same with mu and lambda exchange. So I just add the same as mu and lambda exchange. So I have a gamma kappa lambda mu g kappa mu plus gamma kappa mu g kappa lambda. Right? Everything there is a mu and it's changed with lambda. This is the same with mu and lambda exchange. So I have a minus gamma kappa mu g kappa lambda minus gamma kappa lambda mu g kappa. Okay. Aha! This and this goes down. This and this goes down. These are the same. So this is equal to 2 times gamma kappa lambda mu g kappa mu. So what is left is to multiply by the inverse of the matrix G. Right? So I can define the inverse of the matrix G as G mu sigma G mu kappa is delta sigma kappa. I take this equation and I multiply it by 1/2 the inverse of G. Delta, so kappa turns into sigma. What is left is gamma sigma lambda mu is 1/2 G mu sigma. That's what I have here. dg mu over dx lambda plus dg lambda mu over dx mu minus dg lambda over dx mu. Which is what I promised you. So we express the affine connection in terms of the metric. So if I give you the metric, I can express the affine connection. I can calculate the inverse metric and the derivative, and I get the affine connection. This has another name. I told you that the affine connection has another name and another way of writing. This is also known as the Christoffel symbol. And is denoted with a curly brackets as a sigma lambda mu. Various reasons which I won't get into right now. All right. Oh, we're still surviving. It looks ugly, but it's just algebra. There's nothing much more than that from now. I proven to you the point that I wanted. The point that I wanted is that we can express gamma in terms of the affine connection or the Christoffel symbol in terms of the metric at the first derivative of the metric, which enable me to give the physical interpretation affine connection to be related to gravitational acceleration and the metric to the gravitational potential. We haven't shown any of that, I just said. But of course the metric has got nothing to do with gravity. Now, before we go home, I'll just take 2 more minutes of your time just to help you get a little bit of let's assume Euclidean space, right? 2D example, 2D Euclidean space. I just want to write it not in x, y, but in r and theta. What is the element of length? The s squared.
The r squared plus r squared d theta squared.
The r squared plus r squared d theta squared. What will be the metric tensor? G mu nu. My coordinates. What did we do? All this game that we did, we changed from simple coordinates, psi to x. Now my x coordinates are r and theta. So what is the G mu nu? Remember, we did the x, the y.
Yeah, for the r.
So the r, the theta. So what is the G mu nu? One. 0.
R squared.
R squared. What's the inverse?
1, 0, 1, 1 over r squared.
1 over r squared. So now you can easily calculate the affine connection. Now you see how, right? So if you calculate, now one more thing in homework, I won't give you enough to give you some. You cannot write it in the form of a matrix because it's not a tensor. So don't even try. I'll reduce points if you try to do it. Okay? I have to write down how many different components does the gamma, the affine connection has in this super example.
4.
4.
Oh,
4 to the power of 3.
What values can sigma take?
4.
For this example here,
2.
2.
8.
So it has 8 components. As you can expect, most of these are going to be 0. The only non-zero components after you do the calculation, I urge you to do it, is gamma r theta theta, which is minus r, and gamma theta r theta, which is gamma theta theta r, we said it's symmetric, is 1 over r. Everything else is 0. Okay. So it looks scary, but when you start doing these things, it makes sense. Okay, guys, plenty of things to think about over the weekend. Right? Take a deep breath. I told you already. Now we're starting to dive in. It's not that horrible at the end. It's a lot of ugly algebra, which you have to follow all these small notations, all these indices. But at the end of the day, assuming I didn't do any major mistake here, which I don't think I did, it's pretty much straightforward. Just have to follow the rules. There's nothing else. All right?
Thank you.
Thank you. See you on Sunday. Nice weekend.
השורה שרשמת כאן, היא הייתה פשוט כי ידעת שבסוף זה יגיע למשהו שהיה שורה לפני, ואז ככה כאן.
כן, זה מה שרציתי להגיד.
לא היה איזה קשר כלשהו שהיה, כאילו זה היה סתם איזה תרגיל אלגברי, פשוט...
זה פשוט אלגברה פשוטה. אין פה איזה משהו. שיניתי את החוכמה היא לוודא שאתה יודע לעבוד נכון עם האינדקסים. אתה רואה שמותר לי לשנות אינדקסים, שזה גם אינדקס, שמותר לשנות